Good afternoon, class. So this week we started the motion planning module and starting with lecture 15, we introduce you to some of the definitions, coordinates we need to understand for motion planning. And last time, I think the last section was motion planning architecture. Today, I'm going to cover a little bit in depth into architecture. If you look at this outline, there's two sections. The first section is going to be each module within the architecture, motion planning architecture. And then second part is going to be another type of list of definitions we need to understand to be able to describe, proper space for robot and vehicle to navigate around. All right, let's get started. So last lecture, we introduced you to motion planning architecture, and we did mention these four modules within the motion planner. And the first one was route planning. Second would be behavioral layer, and then local motion planning, and then the control part. But like I said, the control part, feedback control part should be taught separately as a separate module, but in this lecture, we are not going to cover the low-level feedback control. So we're going to discuss these three parts: route planning, behavior layer, and local motion planning. All right. So we did look at some of these examples. How people structure motion planning algorithms, and we went through this summary. Had 4 points, 4 bullet points. Path and velocity planner are usually done separately. There's a scenario-based mission planner. Simple trajectory predictions are often used, and then there's not enough details in the about the interface input-output signals. So those are some of the observations or findings from looking at those examples. And we also talked about some of the considerations when it comes to thinking about research topic. What are the technical challenges out there we need to think about? And then let's move on to the first part of the architecture, which is the global path planning, which is often called as navigation. So as you can easily imagine, navigation is absolutely required. We use it every day if you're driving. And the task is basically finding the global path, getting from point A to point B, destination to origin to destination. And we need we need to find high-level routes, and the solution should provide a desired path, assuming there's no obstacles. And global path planning focuses on travel efficiency, okay? Meaning that how much time and distance we want to basically minimize or optimize time and distance. And when it comes to routing problem. This is very well-studied area in the history, and one widely known problem is the shortest path problem. And people developed different search algorithms to solve shortest path problem. So we want to we want to go from origin to destination, and the problem would be, this would be, origin, and this could be destination, or in the case of, I think this is New York City, and again, origin, destination. We have multiple choices for when it comes to route planning. So we want to be able to plan our routes that minimizes time and distance. And we will talk about more about the search algorithms in the following lectures. But A* and Dijkstra is probably most widely used algorithms. The shortest path problem is static problem, but the link cost can change over time. So that's the tricky part when it comes to finding the solution. And graph search methods can be applied. We'll talk more about graph methods, search methods in the following lectures as well. And like I said, A*, Dijkstra are quite suitable for these type of routing problems. And in addition, lane level guidance would be necessary. So this is basically what navigation is already doing for us, even for human drivers. But when you go with autonomous vehicles, obviously this needs to be done and provide the autonomous vehicle to plan routes to go from point A to point B. But this assumes no obstacles, okay? So this is the key part. So it only focuses on time and distance, assuming there's no, obstacles. But in reality, there's obviously there's obstacles, static obstacles, dynamic obstacles. So how do we handle these obstacles? Which is handled by the local path planning. Okay. And in between global and local path planning, we have this another layer that's called behavioral planning, which is more or less control mode selector. So if you think about the driving scenarios, there are many different types of scenarios. There's lane keeping, obviously, which is most of the time you will be doing lane keeping in lane keeping mode, but you will have to lane change, lane merge. You need to take right turn, left turn. Eventually, when you get to the destination, you need to park. So there are these different tasks, different scenarios that autonomous vehicle needs to handle. And here's the question. And so please think about it. Do you think one planner that works for all driving scenarios? I mean, in theory, yes, human is doing it, but think of it, can machine do it? Can algorithm handle all of these? One algorithm can handle all of these problems? Well, in theory, yes, but practically, probably not. because it just requires so much of intelligence that it becomes a humongous problem to solve. And in fact, the way machine approaches does not necessarily have to be done as humans do. You know what I mean? So, for example, let's say the way we clean room and the way robot cleans the room does not have to be equal. Let's say you're designing robot cleaner and you don't want to create humanoid and make him clean, that's probably not the best approach, right? So if you think that way, basically, so in conclusion, one good strategy would be divide and conquer, meaning that we divide complex problems into smaller problems, and then let different algorithms handle different problems. That way, we can come up with smaller and lightweight controllers or motion planner for different scenarios. But then the downside of that would be there's like infinite number of scenarios. I mean, there can be. I mean, if you want to cover all possible scenarios in the world, right? If you think about all the edge cases, corner cases, if you make that single scenario, then there may be 100,000 scenarios, right? So then now the algorithm starts become not very effective, and we don't even can guarantee its coverage, and there's just too many scenarios and states to cover. So there is these trade-offs, and you might want to think about this when it comes to designing motion planner and architecture. And the behavioral layer actually does this type of job. So you want to sort of group different scenarios into a reasonable number of states, and then each mode or each scenario, we need to design suitable motion planning algorithm for that mode. That way we can hopefully cover 95% of the scenarios that we have to deal with, and still have a sort of logical, very structured, well-structured algorithm with relatively small and light planning algorithms for different scenarios. So that's what has happened in the history, and that's very practically, that's a practical approach, and it's still used in many autonomous vehicles. And so how do we handle multiple scenarios, multiple planners? Well, finite state machine is a robust rule-based mode selector or state selector. And this is an example for autonomous vehicles. So for instance, we may have, lane keeping, lane following, target vehicle following type of scenario. And then we will have to change lanes. If you want to take left, take right, you will need to change lanes to follow the global route. And then and then you will need to be able to handle, roundabout, parking, lane merge. There are these scenarios, and you can make these as a finite state machine logic. That way, you can, and then each state or each mode, you can design proper motion planning algorithm for that mode, for that scenarios. Okay. And the last layer was the local trajectory planning. So just to be clear, if we say, path planning, then it usually means path, means does not contain the information about time or position in time. So when we say path planning, then it simply means, this is the path that I want to take, but the position at a given time is not determined. So if you want to properly describe the trajectory, the path with position in time information included, then a better way to describe it would be trajectory. Okay, so when trajectory planning, when it comes to local trajectory planning, like I said, it's all about obstacle avoidance. Okay, so if you go out on the road, you will see parked vehicles on the road. You will see vehicles, cyclists, pedestrians, kickboards. There's just so many obstacles, and you need to navigate through those obstacles without any safety concerns. So this is, you can think of it this way. So let's say this that red dashed line is the predefined global path that you computed from the global path planner. So you already have that path given to you. And if there's no obstacles, let's say you're driving at night, there's no obstacles around, then you will simply follow that path, that trajectory. But in reality, there's always obstacles, so you need to replan your path or trajectory in given situations. Okay, and that situation can change at any time, right? Dynamically. So we need to replan, and we need to handle static and dynamic obstacles. And this is motion planner hierarchy taken from robotics text or lecture notes. And you can see some similarity between the architecture that we shared, that we introduced, have some similarity with this. As you can see, from map and sensor data, we need to compute global planner and then local planner. And global planner focuses more on the global path from origin to destination, whereas local planner focuses more on collision avoidance. Okay, so in big picture, very similar, but there is obviously there's a difference. Environment is different. Road infrastructure is different, obstacles are different, and so forth. And plus, here, please note that it says this is difficult problem and this is easier problem, but it's the other way around. Usually, when you're doing global path planning, it's relatively easier problem for autonomous vehicle problem. But local path planning can be quite challenging. Okay, This is an example illustration of autonomous vehicle local path planning. When there is a parked vehicle or slow vehicle, then you need to overtake the vehicle by changing lanes. Okay, so we have this lane concept in road infrastructure. And what if it's a double lane, meaning that what if it's a single lane per each side? Then you really need to be careful when you are overtaking these vehicles or obstacles. When there's multiple lanes, then as long as you do not have approaching vehicle in that next lane, then you can make lane changes. But as you can see from this figure below, there's a lane, and we're going to sort of propose path candidates, and then we can do collision checks, and then select path that would give you that would optimize or minimize whatever cost function you are interested in, and then you can select that path, and you need to do plan your velocity for that given path. So this is usually how it's done. Okay. So far we talked about architecture and each layer for within the architecture, and now let's move on to the representation. So we talked about coordinates, but here we are going to introduce you to representation, and there's so that we have common language, and if we want to sort of like math, we need to have same language and definitions, and these definitions and space representation can be very effective and useful when it comes to developing algorithms, or communicating the algorithms with one another. So let's start with this. Okay. Work and configuration space will be introduced. Representation, how the world is represented and understood by the planner is important. Usually some degree of simplification in choosing a representation. By choosing a suitable representation of the world, we may be able to apply existing algorithms to solve our planning problem. Here's a illustration showing workspace and path. So let's say we have this world or workspace, and then there's obstacles in that workspace, which is noted with blue colors. And then there's a free space with gray color. And then we have robots. Here, in this case, it's a point robot. And then we have path we want to plan. Okay. And we have a starting point. We have goal point. And then P of T represents position at time t of the robot. So these are notations and space representation that we are going to deal with. And here's the description of workspace and configuration space. Okay, the world has two entities, robots and obstacles, both considered as closed subset of the world or workspace. So O represents obstacle space and R represents robot space, which is subset of the world. The space for motion planning is a set of possible transformations that could be applied to the robot, considered as a rigid body in this study. Some robots may not have rigid body. And we're going to refer to this as the configuration space. We will have some examples, okay? Important abstraction that allows to use the same motion planning algorithms to problems that differ in geometry and kinematics. Two common views of configuration space would be metric space or topological manifold. So that's that. Like I said, those are definitions, and I'll have some examples in the following slides. The robot is mapped to a single point in configuration space C. Complete specification of robot configuration is Q, which is in the C space, configuration space. Robot's workspace is W with n dimension, and points occupied by robot is A of Q, which is a subset of workspace, and obstacle space is also, it's noted as O, subset of W workspace, and free space is noted as C free, which is configuration space minus obstacle space. Okay. And then we have obstacle space defined as follows. So it simply means, robot should not have any intersection with obstacles. Okay. Oh, I'm sorry. So configuration space that intersects with obstacles. So the free configuration space would be configuration space minus that obstacle space. Okay. I have a figure that shows these concepts. Okay. The workspace is often the representation of the world, possibly independent of the robot itself. Often describes some notion of reachability, what space is free or occupied. Configuration space just describes the full state of the robot in the world. And let's consider a robot is no longer a point, but occupies an space or area. So here is illustration of some of those space definitions we introduced. So we had obstacle, and we have free space, which was noted as the gray, but now the configuration space is going to be this sort of light yellow area. And what this represents is the configuration space drawn in the Cartesian coordinates. And as you can see, that includes the robot space, robot size considered in the space representation. So as you can see, there is these some gray areas that you cannot actually have access to So you should not get into that gray area because of the size of the robot. And here's more examples of configuration space. A robot without rotational symmetry. So if there's a robot with, let's say, long arms like this, then obviously orientation of the robot will be important when it comes to collision avoidance, right? And that has impact on the configuration space. And as you can see in this figure, depending on the robot orientation, you can have different configuration space. So this needs to be now 3-dimension instead of 2-dimension. So if robot was symmetric in rotation direction, then we do not have to have this 3rd dimension, right? But because of that asymmetry, we need extra dimension to describe that orientation part. Okay. Another example. So on the left side, it's a physical space. Assuming we have so let's say there's a 2-link planar robot arm that has to move from a starting point to another to end point while avoiding these obstacles. Okay, this is manipulator type of problem. And on the left side we have physical space, and on the right side we have configuration space. So in this example, configuration space is defined by θ1 and θ2. And θ1 is, I believe this is the angle, and this is the θ2. Okay, so the whole idea is that we can describe this space with the, let's say, actuator dimension. And of course, there is a mapping between the actuator domain versus physical world domain, and the configuration space doesn't necessarily have to be in the physical 3D space. That's the whole point. And by using this configuration space in, let's say, actuator domain, we can if we can come up with this configuration space, then we don't have to go back and forth between 3D space versus actuator space. If we can plan things in actuator space, then we can design a controller directly in the configuration space. Okay. Does that make sense? So in this case, θ1 is θ1 and θ2 would be the orientation, angular position of the link, and we can draw this configuration space. We can define configuration space with θ1 versus θ2, and then we can compute the obstacle space in configuration space. Okay, and those are these areas: green, orange, blue, and purple areas. So And this is so convenient because what this tells us is that the theta 1 and theta 2, which is so let's say we have positional encoder, and we can directly tell that we should not get there, right? We should stay within this space, right? So let's take a look at this example. So starting point was here, and the goal was this point, start, end. And can you tell how we should plan this from the physical space, 3D space or 2D space? Well, this is a simple problem, and you guys are smart, so you can sort of visualize things. And okay, so to avoid obstacles, I should sort of collapse this second link and then rotate and then unfold the second link, right? So you can tell that because this is a simple enough problem, but when things get really complicated, it's difficult, more difficult to solve. And if you want to optimize things, it can be more challenging. But in the configuration space on your right side, this is theta 1, theta 2, which is, you can think of it as actuator space. And theta 1 is your actuating, you're controlling theta 1 and you're controlling theta 2. And this was, this is endpoint. This was starting point. Okay. So if you want to start here and go there, all you have to do is plan your path this way, right? Without colliding the obstacles, okay? And this is so much intuitive, so much easier to design a controller or planner, right? And if you map this configuration solution of the configuration planned solution of the configuration space and map that into 2D space, physical world, then you will get the similar results. What about, is there another solution? Well, this is another solution. So remember, this is configuration space, right? So start, end. So here we took this path, right? But we could also take another path because this is continuous world. You know, theta is 3D 360-degree space that is continuous. And so we can go the other way around and this direction and then this direction. And that's another solution we can find from this configuration space. And that results in this solution, which is somewhat different from this solution. Okay. So can you guys see the convenience of using configuration space? So if you can propose, if you can use a good configuration space, you can make the problem much easier to solve and deal with less. You have to deal with transformation, space transformation, or coordinate transformation problems less. Okay. But the problem is how to compute configuration space, right? Configuration space is not provided, right? So that's the tricky part. So here's some questions to you. First, how to measure obstacles. Where am I? Where is the goal? How to compute C obstacles, C free space. And there are very simple basic principle called Minkowski sum. This simply describes that when you have two, let's say two objects, you can sort of sum those space and put that into the the space side. For example, we talked about here we talked about point robot, right? But what if the point robot was not a point in reality, right? Then you have to consider both size of space or size of the robot as well as the obstacle. And what this Minkowski sum simply states is you can lump that into one side. And so for instance, two sets of position vectors A and B in Euclidean space is formed by adding each vector in A to each vector in B. Okay. And visualization of that is you can sum space of occupied space of A and put that on top of B, and that creates this space. Then now you can consider A as a point. That way you can generate this obstacle space and make your robot a point. That way, assuming, by the way, this example is assuming it's a it's a box in this case. But if it's if it's not symmetrical, then things can become a little more tricky. But anyway, so this is one technique when it comes to computing this obstacle space and make your robots a point. That way you don't have to worry about your robot space versus the obstacle space, and lump that into one side, and then just make your robot position as a point. Okay. Positions in configuration space tend to be closer for the robot. Can be easier to solve collision checks. Allows a level of abstraction that means solution methods and can solve a wider range of problems. Sometimes helps with wraparound conditions. There's a little more information about continuous versus discrete state space representations. But these are not that critical topic I have to cover today. So today I will finish here and move on with discussion session. Okay. All right. Let me stop here.